any property, specific property, between two states which are specified in terms of the temperature and pressure. So this is what I mean by delta U. So if I were to, let's say, locate these states on the TP plane, and we could reach the state from state 2, that is T2, and pressure T2. So this is P1, P1, this is P2, P2. So we could choose either of the many parts, infinite number of parts, but we chose particularly two parts. The distinguishing feature of these two parts being it consists of two segments, each of the parts. One is a constant pressure segment and another is a constant temperature segment. Right? So let's take this, we look at it as part A. Right? And we also chose another part B. So when we choose part A, then we saw that we will be integrating at T1 between P1 and P2. So that will bring it the, if I calculate delta U using part A. So it will be P1 to P2. Now if I want to write the change in property for part B, then you can clearly see that would involve the integral from P1 to P2. Constant pressure, that constant pressure would be P1, and then I have integral P1 to P2. This would be at P2. Basically, part A, I need the coefficient du by dt at T1, du by dt at T2, whereas for part B, I need du by dt at T2, while du by dt is needed at T1. This is what distinguishes the two parts, and we make it that the two answers will be the same. Right? So, and I'm going to prove it directly. They will be the same. So now let's take an example. We look for instance, we start out with the enthalpy. You will see for at least the enthalpy, entropy, and internal energy. You will see that these derivatives would be directly related to the for all functions. Probably, if you look at dE by dP or dH by dP and so on. You see that all of them are related to the equation state. So typically, this integral can be calculated using the equation state alone, and invariably this would require calculation of the specific field, or the require the specific field as the input. For instance, you take H equal to H. What I want is dH by dP, and I also want dH by dT, the constant P, which is nothing but Cp. So what you can see is that if I replace this by H, right? So replace this by H, then for here I need the Cp data at pressure P2. So here I would need the Cp data at pressure P1. So this will determine which expression you use, because the other part, dH by dP, now what is dH by dV? Based on expressions we already have, can you tell me what dH by dP is? it on the board. dH by dt. Yeah, you can bring your notebook. You want you to write it on the board, on whatever you have in your notebook. It's not dH, it is. I just want you to write dH by dP at constant temperature. Not, no. It's clear from here. This is all expressed. Can someone write? Yeah. I don't expect you to remember these, but you should have it in your notes somewhere. It is also given in one of the assignment sheets, the formula sheet. I don't want you to write that. I want you to write this. No, you consult your notebook. That goes to show that you don't have anything in your notebook. You have the expression. Who has the expression in the notebook? Yes. Can you come to the board and write it? You can bring the notebook. I don't expect you to remember it. I don't know why you are making such a big deal out of nothing. Okay, good. Now, any other expression, let us say, yes, this is correct. I am not quite sure this is correct. You have the expression after I don't know it's right. So you have to write it in any other form. I am not sure that is correct. Maybe it is. Yeah, it's correct. dH by dt at t, is it? Constant t. dH by dt you are writing. I want dH by dP. You are writing. That she is already written. First of all, I don't think this expression is correct even. Any other expression? No. You've already had your chance. Any other expression you have in your notes? That shows you can't write it down what I am writing on the board. Any other expression? Yes. D beta that she has already written. Any other expression does anyone have? I derived all of these in great detail, but it doesn't look like you have written down anything. Now I'll write it myself. Well, we can derive it from this. What I meant was an expression like this, b minus t. Now dv by dt can be expressed in terms of, so can this be used directly? Right, in the expression. Suppose now I have, let's say I am using dH by dt. So what would this be? So I have here, the first term I am writing, integral p1 to p2, p minus d, dv by dt, dv. What is V a function of? What is V a function of? T and P, but here it has to be evaluated at T1, right? This is an integral only over P. T1, that's very important. Minus, if you just give an integral like this, it won't have any meaning unless you write explicitly. So this has to be T1 because everything is expressed, and I write this as dP. Now this integral makes sense. I have some function of pressure and temperature. Now if V is a function of pressure and temperature, so is dV by dt in general, right? But I have to evaluate everything at T1. This whole integral is evaluated at T1, or the integrand rather, or the integral itself. And it's an integral only over pressure. So unless you just put V minus P dV by dt integral dv is not a correct answer. So we haven't understood what it means, right? So if I want to, this formula is correct, but if I want to apply it here, it has to be written clearly like this, right? Now there is a problem with this because we know that the information relation between P, V and T we have always maintained is given as a pressure explicit equation of state. That means pressure is expressed as a function of P and T, right? So, but here we have everything expressed as a function of P and T. Volume expressed as a function of P and T. And dV by dt also expressed as a function of P and T. So, now how do we handle this? How do we change this? Because you have to understand that if I am given P as a function of P and T explicitly, right, then I can go ahead and evaluate this integral. But that's not what is given. What I am given is P as a function of P and T. This is what would be given. So given the input is in terms of a pressure explicit equation of state, what do I do with this integral? How do I evaluate this integral? So let me first pose the question, how do we replace this, or what do we replace it with? Minus, I know that dV by dt is minus dV by dt by dV by dt. That I can do. Right? So now, what I have done is I have converted this to a pressure explicit, but now the function, this function is a function of T and B. Of course, it would have to be evaluated at T1, but I have now converted a function into a pressure explicit form, but it is now a function of B rather than P. But this is an integral over P. Right? So how do I convert the integral over P to an integral over V? How do I convert? What? Substitute for P, right? So now I have to make use of this transformation. So if I make use of this transformation, so this is what will convert an integral over P into an integral over V, right? So now I have to write this as what happens? Let's write it as two terms. So this now, instead of P1 to P2, I am going to get an integral over volume. So I have to change the limits also. For instance, if I have integral A to B f of x dx, so this is clearly x equal to A and x equal to B. Now if I make a transformation, x, which is a function of u, I can make that. You must have done a lot of these integrals. For example, using trigonometric transformation, you can evaluate certain integrals very easily, right? You might have done that. So now what happens to this integral? Now this is an integral over u. There must be some reason for converting it, and often it's a ease of calculation of one integral over another. Two are equal. So this will be UA, that means the value of u at x equal to A. Because the integral, everything has been changed. It's now an integral over u. So I have to integrate from UA, which is the value of u at x equal to A. And similarly UB. And so in this integral, wherever I have x, I have to substitute it by the function which expresses x in terms of u. suppose let's say x equal to u square or u cos u, let's say. Wherever I find x, I have to put the function and express the integrand in terms of u. But there's another term or another factor that would be part of the integrand. And what is that? Dx by du, right? We cannot ignore that. So everything has to change, but on top of it, it's not enough. It just change the variable of integration and the limits and the function. The theorem of integral calculus says that on top of the function, you will get another factor, which is simply dx by du. That has to be incorporated. So let us now take the first term. Integral p1 to p2 will now become integral p1 to p2. Right? Integral p1 to p2. And now I have p, right, which is a function of p and t. So how do I change that? Right? So we now have, what I have here is integral p1 to p2, p of p, p1, dp. How do I change this? Let's now take the second part, right? The second part is easier to change. Right? First I take that. So I have integral p1 to p2, right? Where I have p1, or rather minus t1, right? And then I have minus dp by dt expressed as a function of dp by dp expressed as a function of p. Right? So the minus will cancel with the minus. So I have this, and then I have dp. So I make it p1 and p2. So I have converted the integrand, the function itself. The function is t1 dv by dt minus t1. So I take that. So I want to convert this to a function over volume. I have done that, right, by using the implicit or inverse function theorem. So now I have converted this to an integral over b. But one more factor is there. What is that factor here? dp by dv evaluated at t1. That's very important. It's just a generalization of this rule. Here, they have to now recognize that even though the integral over p is converted to the integral over v, the p is a function of v and t. But here, evaluated at t1, this is why we can use the single variable rules here. Basically, single variable transformation. But temperature is important. I cannot substitute any other temperature. Right? So this would be dp by dv p1 dv. Now p1 and p2 are the volumes at the two states. Now for the whole of this integration, everything is at t1. So clearly p1 is so I have to actually calculate P1 and P2. So even though I get the temperature and pressure are what are specified, which is a common specification, now I find that because the way in which the information is given to me, which is a pressure explicit equation of state, I am now forced to find the volumes corresponding to the two states. Right? This is actually, I'm sorry, this is here. T2 or T1? It's a T1 only. Right? Because we are actually here P1 to P2. So we are continuing to remain at T1. That's very important. P1 to P2. So the volume will here correspond to T2 but evaluated at T1. So everything is, so it's not really the volume of the final state, but it's rather the volume of the intermediate state, because this integral is everything is at T1. So we are only looking at this segment, right? So this is from T1 to T2 at T1, right? So now I have to calculate the volume, specific volume corresponding to that, because the transformation is important. Is this? It's not T as a function of T and T arbitrary temperature, but at T1. So clearly, when I say everything has to, so if I put T1 here, right? So T1 is what satisfies this equation. Similarly, T2. So I'm sorry, T1 continues to be. Sorry. So this is V2. This is V1. This is what I mean by V1 and V2. It's now converted into an integral over V, and conveniently this cancels. So I'm left with the T1 is there outside, right? So I have just this integral. Now how do I evaluate this integral? Right? So you have to know, I can do the same thing. dP by dP I can substitute, right? dP. But I will use another form of what is known as integration by parts, and write this as integration by parts as usually two forms. One is, suppose I have integral a to b f of x g prime of x dx right? By integration by parts tells me that this is given by fg, the product evaluated between the limits a and b. This is what the formula takes. I am not going to prove it, right? So what this means is that this is f of b, g of b minus f of a, g of a. So the product f, and not g prime but g, right? So if I have the product of two functions, right, one of which can be expressed as a derivative of another function g, right? So I get this, but minus, and the derivative gets reversed, and now I will have d of x, f prime of x dx. But I am not going to use this form here, but what I am going to use is another famous common form which is sort of misunderstood often, and that is f expressed as a function of g, right? This can be written as fg again between, let's say this is between limits a and b. So this is again between limits a and b minus integral g df, right? So this is a very famous form. It's often written as integral u dv is bu minus integral v du, right? So that's the form that I will use here. And so this can be easily written as dp between states, right, 1 and 2 minus integral p dv, right? So p of dt1 dv. This is what I have. So how do I now evaluate this? So this is nothing but P2 minus, so this can now be written as P1 to P2. So P1 and P2 we have already explained what they are, right? And so I can gather together all the terms and write this as P2 P2 minus P1 P1. That's what I'll get there. Right? So just the portion of the integral alone for u equal to h, right? So dV from V1 to V2, right? And then I have another plus P1 integral V1 to V2 dV by dt dV1 dV. So now all of this is this portion for u equal to h. By choosing path A, I have calculated all of this. It's a fairly long-winded formula, and I still have this left, so I can write delta h evaluated out of path A as all of this. Now, first thing I have to recognize is that you can easily see that all of this can be evaluated if I am given an equation of state of the form. Let's say the van der Waals, let's say, is given. Right? So you have to verify whether I can calculate all of these quantities. Right? So now P1 and P2 are given to me. Right? So P1 and P2 I have to calculate. That would mean solving this cubic equation of state it will turn out. I have to solve. Right? And we have to see the implications of this being a cubic equation of state. We'll see that later. But in principle, I can solve, substitute P1 and T1, and whatever I get out of this will be V1. Right? And when I get P roots, then I have to decide which one is the correct root. That we'll see later. Again, by substitute P2 and T1, whatever I get out of solving this will give me P2. So I can find both P1 and P2 in principle. We'll see later on how to do it practically. Right? We can get that. Now go to this. Once I've calculated P1 and P2, the integral can be easily evaluated. Here very easily, analytically also you can do it. More complicated equation of state, we can easily do it numerically. Right? Again, once dP is given, P is given, dP by dt can be calculated. I can evaluate P1 and evaluate that integral from P1 to P2. So everything here corresponding to the first term, dH by dt, that integral, even though it's a somewhat lengthy formula, everything can be calculated once an equation of state is given. Right? So that much is clear. Now what about the next term? So this would be plus integral T1 to T2 Cp, because dH by dt at constant pressure is Cp, and so I need Cp at a pressure P2. Now normally, especially for gases, the Cp will be a strong function of pressure. Right? So you cannot ignore it completely. So it depends on whether you have data available at that pressure or not, which might not always be feasible. Right? But then you can ask whether I can use this formula. Right? If I use this formula, of course the formula will look different because now everything here has to be done at T2 rather than T1. Right? Because the whole integral over P will happen at T2. Right? And on top of it, I need Cp at P1. So between P1 and P2, it's a question whether Cp data will even be readily available. Right? So what I want you to know is that even though the specification may be in terms of T and P, it has actually more, we are forced to work in the dV domain actually. Everything is done in dV actually because we had to convert it to an integral over V and evaluate the corresponding values of V at the states required. Right? So given the lack of Cp data, which is not readily available usually at any pressure you want, the data might not be available at either of the two pressures that correspond to your initial and final state. So we can choose a third path, which I will now denote as path C. What I will do is I'll start from P1, T1. I'll go to a very low pressure P0. So this will look like a roundabout path, right? So I go to a path P0, then I go all the way up to T2 at P0, very important and textbooks normally do not mention it. We are assuming implicitly that there is no change of phase during any of the paths. Whatever path we might choose to reach one state to another, we are assuming there is no change of phase. Because if there is a change of phase, then I cannot do this integration continuously. We have already seen, except for the specific Gibbs free energy, that is equal to the chemical potential, and between two phases the chemical potential is equal by the criterion of equilibrium. All the other functions, be it H, A, B, S, all of them undergo a change when there is a phase change. So if there is a phase change in any of these paths, we cannot just arbitrarily integrate. We have to stop at that point, calculate the phase change, which we haven't seen how to do at all. The phase change property and then do it. So it is assumed when you are integrating sort of continuously as a smooth function, it is assumed that these functions are not having any discontinuities, right? Because there is a discontinuity in H during a phase transition. So we are assuming implicitly that there are no phase changes. So the same holds here also. We see the implication of that, right? So whatever we have done so far has a certain limitation, right? Now what we can see is that whatever we have done, let's say between this and this, right? It might be entirely in the liquid state or even the solid state. That is fine, right? But normally those solids, these equations of state do not represent solid states very well. So basically we are dealing with liquid and gas states or combination of the two. So this might be entirely liquid, but we know that sufficiently low pressures, everything will become a gas, right? And we are going to take actually the limit as P goes to 0. So if we impose the same condition, then we are essentially assuming that there is no change in phase, that means we are entirely in the gas phase. We will assume that, right? So what I am going to now do, right, will include the assumption that we are entirely in the gaseous phase, and we later on see how to handle the transition to liquid phase. So for simplicity, I will assume that I am not encountering any phase change in any of the paths. So since I am going for the path C sufficiently low pressure at which all possibility the substance would be in the gaseous state, and so we assume that there is no change of phase at all. Both the states actually here also correspond to states in the gaseous phase, right? So once we have clarified that qualification, so I am now going to calculate for part C the change in any property. So let's now go back to any property and calculate it using part C. So first I need to so we are still calculating U of P2 P2 minus U of P1 P1, but now choosing somewhat roundabout path, right? So first it will be P1 to P0, right? So that would be, I can write this as U of P2 P2 minus, right, U of P0 P2 plus U of P0 P2 minus U of P0 P1. So that would take care of this segment, right? And again plus U P0 P1 minus U of P1 P1. Right, so U of P2 D2 minus U of P0 D2, right, will be very easy to evaluate. So that would be integral du by dv from P0 to P2, right, and one would be du by dt. So the evaluated as P naught. Now this would be from P1 to P2, and then I have plus integral P1, or I can make it minus P naught to P1 du by dt. So these integrals I know how to handle, right? So let us evaluate it using the equation of state. Now let us take the limit as P naught goes to 0, right? You take the limit as P naught goes to 0, that's what I now denote as C. The C is now written after taking the limit as P naught goes to 0. So this would be equal 0 to P2 du by dt. You see the advantage of this, du by dt at P0 dt plus integral P1 to 0. Now I wrote this as a general, but now I take u to be h, let's say. So when I take u to be h, this will now become Cp at t P naught, limit P naught tends to 0. So now I am choosing a very low pressure in the limit of P naught goes to 0. What can I replace this quantity by? At sufficiently low pressures, every substance will behave like a what? Like an ideal gas, right? Even any substance you take, sufficiently low pressure, so we are taking the limit all the way up to P naught goes to 0. So we can now replace this by Cp Ig, which will be a function only of temperature, that we know. Because we are taking the limit as P naught goes to 0. So the pressure dependence falls apart. We know that for the ideal gas Cp is anyway dependent only on T. So that is what will make this part, even though it is somewhat roundabout, right, to make this part always useful, because the Cp of the ideal gas is readily available. You might have encountered in Thermodynamics book, there will always be a table which expresses the Cp as some A plus Pt plus Cp squared and so on. And you will see the values of A, B and C are given for various substances. That means, as I pointed out, even though it's all the ideal gas, the ideal gas has certain common properties. And depending on which substance it is, the Cp values will change. So for each substance, I have to, depending on which substance is undergoing this property change, I have to choose that substance and calculate its ideal gas specifically. So the availability of data of the ideal gas specifically would mean that this part, even though it's somewhat roundabout, is a more useful from a practical point of view. Right? Now, it is conventional. Because this is a long-minded formula, you will see that both of these are more or less the same. One is P0 to P2, evaluated at T2. Another is effectively P0 to P1, but evaluated at T1. So this is entirely an evaluation from P0, pressure 0 at the second state. This is evaluated from P0, which between P0 as the first state, right? So instead of writing these lengthy formulas, it is often conventional to introduce what are known as the departure functions. That's an important idea, but all of this discussion so far is to motivate the concept of departure function and its utility. Right? So what do we mean by a departure function? Departure function is defined as u minus uig. So there are two types of departure functions we can define. One, at the given temperature and pressure of the substance, or the given temperature and volume. Now, I have fixed the substance what I am doing. So I am now going to move away from two states of the substance, but focus on only one state. Right? So what is that state? I will take that to be T1, P1, V1. So one particular state of the substance is all I am going to focus on, but I am going to focus on its departure of any property from the corresponding ideal gas property. Right? So either I can specify T1, P1 or I can specify T1, V1. So there are two common specifications. But they are all related by P1 is equal to. Now there is no more confusion about what P1, P2 is. There is only one state I am focusing on. So I am going to either look at T1, P1 or T1, P1. So what does it mean? It means for any property, I look at the property corresponding to the actual state and specify, and this is the difference with the ideal gas property of that substance. The ideal gas of that substance evaluated at the same specification. Now it will differ depending on whether it's T1, P1 which is specified or T1, V1 which is specified. The departure functions may differ. We'll see why that is the case. So you have to clearly remember that all of these correspond to the property of the substance. It has a certain pressure P1, it has a certain pressure T1, and it has a certain specific volume V1. This fixes one state of the substance. Now what is interesting from this is that either this or this can be calculated directly from an equation of state alone. So we don't have to worry about Cp values. Right? We can easily show that the departure function for any of the properties A, H, E and so on can be related to the equation of state. Now my objective hasn't changed. Still I want to find, let's say u of T2, P2 minus u of T1, P1. So how am I going to find this from the departure function? I will evaluate the departure function as u minus u ig of evaluated at T2, P2 minus the same departure function evaluated at T1, P1. Because when evaluating at T1, P1 and I have the formula, all I have to do is to replace T1 by T2 and P1 by P2. Right? Then I will get the departure function at both the states. Right? However, what I want is u of T2, P2 minus u of T1, P1. That is there, but I have now added and subtracted two other terms corresponding to the ideal gas property, right? So obviously I have to add and subtract those corresponding. So clearly this is uig. I have subtracted that at T2, P2. So I have to add that minus uig. So I can write delta u now as delta u minus uig plus delta uig. Now you will see this is just an indirect way of representing the path C. Because what you will find is when evaluating this, you will immediately require only the specific heats of the ideal gas corresponding to that substance. So this is an indirect way and a more compact way of representing the required formula. So the two conveniences. One, the departure function requires only the equation of state. So what I am doing is, I still require two inputs, the equation of state and the specific heat. Right? But now I am calculating the departure function using the equation of state alone. So basically I am calculating the change in the departure function and splitting this change into two parts. One part that requires exclusively only the equation of state, and another part that would require the properties of the ideal gases and would automatically include the ideal gas specific heats which are commonly available. Right? So I'm splitting this into two parts. So now let us see how the departure function can be a formula. So whatever I have done here might have been somewhat disorganized, because what I am going to do systematically is only the departure function. So then you can recover all the formulas that we had written earlier. Right? We will focus on one state and the departure function corresponding to that state, from which I can calculate the departure function in any other state, and depending on that I can use this to calculate the change in any property. So are there any questions? If not, we will take up the formula for departure functions, how to derive them in tomorrow's class.